Okay, good morning. Um, ah, yeah. So, welcome to the 43rd Nmrg meeting. You probably all know that Nmrg is a research group on network management. And we are organizing this workshop here on measurement-based network management for already the sixth time or seventh time, I'm not sure. So we started originally with looking only at net flow or fixed-based network management, and we still for 2 years we extended to general measurement-based network management. So this is we call it a workshop. So we have 6 speakers giving insight in the current work on using network measurements for network management. And of course, this is not a conference here, so we hope that there will be a lot of interaction. We have asked the speakers to give enough time for questions and for discussions. And first of all, I want to show you this not slide here, which you probably already know. So you can probably also find it on the IETF homepage. Well, sorry. Oh, that's the one I got from the Nmrg chairs, from the Nmrg head. Okay, then you gave me the wrong one, indeed. So, our agenda is, currently we have welcome speech. I mean, these 2.5 hours are not structured in any way, but we plan to have a meeting. We'll have 3 presentations before the break. Then we make a break. The duration we choose ourselves. And after that, we will have 3 other presentations, and then close at 12 o'clock. Something I forgot to tell you. So this workshop is organized by me. I'm from the University Catholic the UCL, the Belgian UCL, not the London UCL. Colin Schmidt, who cannot be present today, and the Nmrg chairs or heads or leaders, Laurent and Lisandro. Lisandro was around. Probably yesterday. Okay. If there are no other questions, one other thing. There is another Nmrg meeting on Thursday on a different topic. So if you are interested, please join. So I would suggest that we start with first speaker, who is Tiffany from Bonn University. So we didn't have a long trip.
So, good morning, everyone. I'm Łukasz Kekeli from CESNET, or Brno University of Technology. I'm a PhD student, and I'm here to speak about our attempt to accelerate IDS systems for high-speed networks. As I already mentioned, I'm from CESNET, more specifically. So, as I already mentioned, I'm from CESNET, Czech National Research and Education Network. More specifically, I work for LibRouter Group, and our main goal is to monitor the perimeter of our network and to guard that perimeter from external or internal attacks that we can detect from monitoring these lines. So we have WASP toolset, to do so from network probes, so data acquisition from network lines, through collection, detection, storage, visualization, and remote configuration of the whole. In this presentation, I want to speak about network probes and how we collect data and how we analyze the packets. So the standard approach to monitoring probes is you have a network interface card that provides packet capture, and on those captured packets, you do some software processing on a CPU of a host server. This is the standard approach. We have an accelerated approach when the probe itself has an accelerator in FPGA, and this accelerator can somehow aid the processing of the packet. So the software performs only very specific or very advanced processing tasks, and the card can accelerate the total throughput of the system. We call this concept software-defined monitoring. The concept is here on the right, you have your processing applications, your flow exporter that exports NetFlow data in IPFix or NetFlow formats. It receives data from the card, and in the card receives packets from the line, and don't send only whole packets to the software applications, but the software applications can instruct the card to do some processing. It can either parse the packets and send only headers instead of whole packets, or we have flow cache in the hardware, so some kind of NetFlow records or aggregated records for flow can be also sent to the software instead of whole packets. And as I said, this is all controlled by the application, so it's flexible. Depending on application, you can have different requirements how this data should be pre-processed. So we measured the achievable speedups on various network monitoring tasks, and we proved for standard NetFlow we have like 5 times speedup. For application layer processing, mainly HTTP processing, we have speedup to like 3 times compared to the standard monitoring probe. But when the software need to process every packet, we already published those results at the Infocom conference and in IEEE Transactions on Computers journal. So now the question is, can we use this system, this software-defined monitoring system, to accelerate also IDS? So not only network monitoring, but IDS. So our assumptions are that current IDS systems are not fast enough for current high-speed networks. Also that default discarding method that they use, basically blind discarding when you have an input buffer, and if the IDS is not fast enough, this buffer starts to blindly lose packets, is not good for the detections of IDS. And informed discarding can be better, can perform better. So another assumption is that usually the attacks or the threats are present in the initial packets. So usually you don't find a threat inside in the middle of a, let's say, a long video stream, but somewhere in the beginning of each network connection. So and the last assumption is the heavy-tailed character of flow sizes or network connection sizes, when you have very few heavy flows that carry majority of all the network traffic. So by dropping only the middle packets of these few heavy flows, you can get a pretty decent reduction of total network traffic that is processed by the CPU. So these are the assumptions. Using SDM, basically, to accelerate IDS, we use SDM as a pre-filter, so we don't need a flow cache in a hardware. Our application is IDS, but the system stays the same, basically. It's only a different use case, so we don't need to modify the SDM concept. We just use it for new use case. So our test setup was, we have 2 servers. Sorry. We have a traffic generator with large pcap files on an SSD drive, which we replayed but using TCP replay over a standard network interface card. These are backups collected from our network, so that it's a real traffic. It's not synthetic, it's real traffic. So the replay traffic was then delivered to our acceleration card. In that card, we have an SDM firmware, so the hardware acceleration part that forwarded packets to IDS software. And the software instructed the SDM to do the prefiltering. We tested two IDS systems, Suricata and Snort. The testing server, just a quick stats. We've got two physical Intel processor with total of 16 cores at 2.6 gigahertz, a lot of RAM, and of course our acceleration card with SDM firmware, as I already mentioned. So with the acceleration, with the accelerator on the FPGA on the card. So for some results, first of all, it's Snort over standard lib backup interface. Now to describe the graphs, on the x-axis of both, we have a speed of the input link. So here it's from few hundred megabits per second to 2 gigabits per second. And on the higher graph, we've got buffer overflow percentage, so percentage of blindly lost packets on the input of the IDS system due to its lack of performance on given speed. And on the lower graph, we have number of detected events on that speed. The pickup was the same, so the number of detected events should be same if the detection is 100% correct. But due to, we can see from the graph that due to blind loss of packets, the number of detected events is decreasing also. So if we take a look, the green line is the IDS Snort without our acceleration. So pretty quickly, even at 250 megabits per second, the drop rate starts to rise, and therefore the detection rate drops. Using our accelerator, the drop is around 0 up till 3 times larger speed, so up till 750 megabits per second, and then starts to slowly rising as well. So the detection rate is better than without SDM. So this is what we want to achieve. Better detection rate, so the IDS need to process only packets that are interesting and therefore can detect more threats. Another similar graphs, but this time for Suricata over lib backup, we can see the same trend basically. Without SDM, the drop rate starts very quickly. With SDM, the drop rate is not so significant, and also the number of detected threat is not declining so rapidly. So we can use this IDS on even higher speeds with more precise detection rates. Now the lib backup has a problem with performance that is known, so we try to use our own driver instead of lib backup, which bypass the kernel, do zero memory copy and so on. So basically the card delivers packets directly to the application, in this case to the Suricata IDS, and the results are better. The performance is now in terms of gigabits per second, and again we can see without the acceleration, the drop rates start to increase very quickly, and the detection rate start to drop accordingly. And with SDM, I'm sorry. With SDM, we've got better results. We've got more detected threats, more detected events, even at higher speeds. And the last graph is basically just the Suricata, the same IDS, but with a smaller rule set. For the previous test, we use all the rules that are available. For the Suricata, it's like 13,000 rules. But for this test, we reduce it only to malware detection. So the number of rules was only 1,000 or something like that. And the performance is even better, even more than 10 gigabits per second, up to 20. And we can see basically the same trend. As the drop rate is increasing, the detection rate is decreasing. And again, with SDM, we've got better performance, better detection rate. So to summarize, IDS can be accelerated using our SDM system. With reduction of packet loss, we increase the accuracy of detection. So from the other side, the SDM is applicable not only to network monitoring, but also to network security, specifically IDS acceleration. And we are preparing another Infocom paper about this acceleration. So this was just the preliminary results for this paper. So thank you for your attention.
So, any questions? Please go to the microphone. No. Ah. And present yourself and your association.
Hello, this is Jochen Kögel from Ethernet. As I understood, you drop the middle packets on
Yes.
the flow for speed up. Can you tell how many packets do you need, and is it a fixed count of packets you need from the start of the flow, or does it vary?
We have a variable threshold on which packet we start to drop, and it's usually around like first 20 packets are analyzed, and then we start to drop, or 30 or 10, but usually it's between 20 and 30.
Okay, did you play around with this parameter, and does it
Yeah.
impact? Okay.
If we play around, basically after 20 or 30, the number of drop packets is basically declining, but the number of detected events is staying the same.
Okay. Okay. So, but if there's a download with a bunch of files,
Yes.
and the second file is maybe with malware, then it's maybe a problem.
Yeah, maybe.
Okay.
But as I said, we try to play with the parameters and look at the graph or look at the data, look at the results, and we kind of wasn't able to see that kind of behavior in our data.
Okay, so can you tell, is it the malware detection, is it more like web traffic where you detect it, or is it mostly large downloads where this effect is more predominant?
Most of the traffic on our network is HTTP or HTTPS, so it's usually web traffic.
Websites and
Yeah.
websites.
Good morning. Thanks for the presentation. Artem Gavrichenko speaking from Curator Labs. You just mentioned that a lot of traffic in the network is HTTPS. What does the solution has to do with encrypted patterns?
I don't actually know the insights of the both tested IDS, so I don't know if they do some or what kind of analysis they do. We just take the IDS and.
As per Snort, it doesn't support going into the TLS session.
But
only
I think that
parameters and ciphers.
I think that some threats can be detected also on the parameters of this traffic, if I'm not mistaken.
Okay, see, thanks.
I have a question from a remote participant, Ricardo Schmidt.
Okay.
He was asking how easy it is to program this system. Is it offering an API, or do you need the entire source code?
Well, I mentioned Snort and Suricata. Snort has a limited support of some extensions. That's why we only tested it so far with standard libbackup interface. But for Suricata, you can implement your own plugins, basically input plugins or some different kind of plugins that can take the data for you and do some reprocessing with them. So using the plugins, using the API that is already in there, we was able to extend the system with SDN acceleration.
But let's say you have your own ideas. How hard would it be to adapt it?
Well, our SDM system has its own API. So basically, you just have to call a function to connect to SDM, and then call a function like, I don't like this flow, drop it for me, for each flow that you don't want. And that's all.
Any other question? No? Okay, thank you again. Then I would like to ask the next speaker to come. It's Abdul Kader from India. In the meanwhile, could one of you take care of the Jabber room and see whether there are questions coming up from remote participants. Will anybody do that? I tried it with my Windows PC, but it's hopeless. This looks strange. Anybody willing to go to the Jabber room? Giovanni? Thank you. We have a.
I'm Abdelkader Labadi, Associate Professor at the University of Milan. And I'm going to talk about the work that we published last year in UPS, workshop for forensics. And yes, of course. And the work is about topological analysis and visualization of network monitoring data, where we have a case study, which was the darknet traffic. The overview of the presentation. First, they will present the motivation of the work. Second, they will present some background and related work, the methodology that we applied in this work, some experimental results regarding the scanning activity and DDoS activities of the darknet, and finally conclusion, future work. So the context of the work is where we are focusing on network monitoring data, which is usually used for security, forensics, and anomaly detection. The goal is to identify malicious activities regarding the traffic patterns behind that, and the alerts that trigger these malicious activities. We focus on a specific part of this monitoring data, which is IBR, network background radiation. Basically, this data is coming from network telescopes, darknets. Usually it's noisy traffic, but important source of forensics data. We have many information that we collect through these network telescopes and darknets. The data is with a considerable volume and wide range of services and sources. The extraction of structure and compounds of this data is difficult because it's noisy and incomplete information. We have all the packets. We have not flows because it's passive. So we just receive packets from the internet. So usually the goal to study this kind of traffic is to predict and model internet malicious activities, basically large-scale scanning activities, or DDoS, denial of distributed denial of services. So to show an example of the darknet, so usually it's a traffic sent to unused IP addresses. We haven't the service behind, it's just an IP address is exposed to the internet. So there is no productive traffic, no legitimate traffic. We are in our lab, we are hosting darknet, so we silently collect all incoming packets without replying to them. So as we show in this example, for example, we have teams of distributed botnets. So the attacker will control the victims and start sending some packets, and this is by the which is the set of unused IP address. And behind this we have the sensors, it's a collector to collect all the packets, and then we are able to visualize them and analyze them. So our goal is to analyze this traffic, which is usually noisy but contains some useful information regarding large-scale scanning or large-scale DDoS activities, denial of service. So the problem that we addressed in this work was what are the compounds or the patterns of the darknet traffic, and how to filter this traffic to extract types of malicious activities, basically to extract DDoS activities and to extract scanning activities. Some work was done before, many work has been done regarding this issue, mainly to characterize internet background traffic. The first work was done by Pang et al. In 2004, where they characterized IBR traffic, basically the composition of the observed protocols and ports in this traffic. Another work was done by Moore and co-authors in 2006, where they studied the probability to observe DOS attacks with the telescope. And Wistrow and co-authors in 2010 made another work to characterize internet background traffic over multiple darknets to extract invariant features and level of pollution of destination IP addresses. This is the first part of works regarding the characterization of IBA. More works where they focused on darknet data, basically the work of Fashka et al. 2016. And other work regarding DNS queries in 2015 by also the same authors, Fashka and all. Regarding the visualization, some work that was done. Basically, there we find some tools regarding mainly INetVis, which plots darknet data on 3D scatter plots, or some 3D visualization tools to monitor and to visualize this darknet traffic. Our work is a little bit different because we applied new technique. This technique is based on topological data analysis. It's TDA or TDA. It's a branch of mathematics where the goal is to study high-dimensional and complex data by extracting invariant geometrics feature from this data to discover relationships and patterns. So the goal is to study large-scale data, multidimensional, to extract invariant or geometric invariant. The TDA has some fundamental properties, very interesting, which are the coordinate invariance. So does not depend on coordinate system. Analyze, which in our case is interesting because we can analyze data collected from different platforms. It is deformation invariance, so it is less sensitive to noise. Even the data is noisy, there is no problem with this data. We can apply TDA, and it is able to handle approximate data. And the third point that we obtain using TDA, the compressed version of the data, the compressed representation. So basically, we'll obtain graph. So let's take an example. So here, our example is not related to networking, but we take 3D shape, which is the rabbit of Stanford, shape. And here we have as input data a 3D point cloud, which with many number of points. In this case, we use the filtering function, which is the eccentricity. So this function will allow us to add another dimension to the data, and on this dimension we will filter the data. It's a filtering function. I will explain later this function. And the output will be a network or a graph. Here it will be 19 vertices and 18 edges. That represents the rabbit. So this is the topological representation of this 3D shape. And the colors represents the filtering parts, the colors of the filtering function applied to the points. For example, so this blue part represents the main body of the rabbit. Fantastic. This is the other part of the rabbit, which is part of the graph. The other part, which is the head of the feet. This is the last part of the object, which represents the bottom or the top of the ear of the rabbit. So this is the main idea. So here we have 3D shape, and we want to apply the same technique for the network packets that we collected from the darknet. So to apply TDA in our use case, so we extracted some noisy traffic monitoring data from the darknet that we hosted in our lab, and we applied one technique from the TDA, which is the mapper algorithm. The mapper algorithm, as explained before, will allow us to obtain this topological graph, this graph that represents the data instead of many points. So the processing steps, so we have the darknet, we have the traffic that we collected. We extract some features related to the packets, basically the source IP address, destination IP address, the ports, and this stuff. We compute the distance between the packets, we use a filter function, same as the eccentricity, for example, but we can use another one. And then we find some intervals to split this function. So we split the values of the function using many intervals. And finally, we apply the DBSCAN clustering technique like DBSCAN to cluster each data in each interval. And then we get this graph, which is topological representation of our data. So this is the details of the mapper algorithm. So the input is the feature vector, which contains the feature of the packets from the darknet. Basically, in this case, we use the timestamp, the source, destination IP addresses, and the ports and the protocol, TCP or UDP. The parameters of the algorithm are the number of the intervals that we use to split the values of the filter function, and the overlapping percentage over these intervals, because we can define an overlap between the intervals, which represents something like a zoomer. When we want to zoom the graph that we will obtain later using this algorithm. In this case, we use the sample filter function, which is the identity. So from the 6 features, we have projected the same 6 features. But the technique is really flexible, so we can use another types of filtering function. And then we will put the data, our data from which are the package or feature of the packets, use over the intervals that we define on the filtering function. And then finally, we cluster each B that we obtained from the interval using the DBSCAN clustering technique. We can use another one, but in this case, we use the DBSCAN technique. And finally, we create this graph where each vertex is a cluster of a beam, a cluster that we obtained using the DBSCAN, and the edge represents a no-empty intersection between clusters. So when we apply this technique, we obtain the graph where each vertex is a cluster obtained from the DBSCAN, and the link between them means that there is no empty set, no empty intersection. So we applied this technique using the DBSCAN. So each interval, the filtering function, and each points projected on this interval, we applied the DBSCAN, which requires 2 parameters, the known parameters of the DBSCAN clustering technique, mainly the epsilon, which is between 2 points to be considered in the same cluster, and mean points represent the number of neighbors that the point should have to be considered as a cluster. And the distance function that we used in this work is the difference for timestamps attribute. For the timestamp attribute, we take the difference. And for IP destination and source addresses, we also take the difference. And for the ports and the protocols, we use the equality, which means equal or not. So it will be 0, 0, or 1. So it's this function that we use, but we can use another one. So we applied this technique over some data to darknet. We take, for example, 1,000 packets. This is the parameters that we use, and we extracted some patterns. For example, this is an example of patterns that we extracted. Here, the large green dots represent scanning activities, where we checked this manually, and we found that these are scanning activities. The red compound represents telnet and SSH access activities. The orange represents some sparse scans, and the yellow compounds represent some randomized and noisy scans. But all of this was checked manually after doing this Then we applied the technique in some data. We have 8,000 packets. This is the parameters that we use, and we are able to extract some scanning activities from the darknet. And we applied also Sericata on the same data, and we observed that we are able to detect more than Sericata. In this data set, Sericata detects only 4 scanning activities, but we have more than 4 scanning activities using this technique. The parameters are estimated using the trial and error method. So we have tried until we find something interesting. And but when we find them, it remains stable. So we can apply them to more data sets and we find good results. Another example of data that or activity that we extracted is regarding DDoS. So we apply this some UDP packets, DNS packets, also that are from that IP address. We use these parameters, the epsilon and the midpoint and the overlap for the mapper, and we are able to find some patterns of DDoS activity, extract them directly from the darknet and visualize them using two planes, where each plane represents the IP address, ports from the destination and the source. Regarding the performance of the approach, so for example, for 1024 packets, it takes less than 1 second to analyze them using the mapper algorithm. To analyze 3 million of packets that we received for 1 day of .NET requires 11 minutes, so which is reasonable. So we can analyze the whole day with this time. We can apply this technique, for example, to know what an attacker, one specific attacker sent today. For example, we can analyze this set of 100 packets in 2 minutes, so we can know exactly what the specific attacker sent through the darknet and analyze this in a short time. But we need to increase the performance, because here we are using a single machine, so we can use more computing power and also parallelize the tool to enhance the performance of the analysis. So, as a conclusion and future work, so in this work we presented this new technique that we are using to extract patterns from a darknet traffic. Basically, this technique used two functions. The first one is this filter function to represent one or more dimensions to filter this data and apply a number of intervals and an overlap over these intervals, and also a partial clustering using DBScan or another technique. The goal is to extract some activities, basically scanning activities or DDoS activities. And as a future work, we want to include more packet attributes and apply this to NetFlow, for example, not only the packets from darknet, and extract more activities and also analyze them. So that's it. Thank you very much for your attention. And if you have your questions, or questions, I want. Thank you.
Hi, Stanley, UFP. So why didn't you use statistical feature extraction like principal component analysis or singular value decomposition instead of TDA?
This is the usually question we have. Yes, very interesting. The first point that we want to validate this technique. This is what we want to do in this work. We know that TDI was applied in different fields, basically for seeing biological data and 3D shapes. And the goal was to apply this technique and validate this, how to apply this and validate this technique on different types of data, basically data from networking. And we want to know more on this validity. How basically it's clustering. What we do here is to cluster this data, but it is more because we clustering in each interval. It's not a global clustering. So also this one for the reason that we want to validate and we obtain the good results. But I agree that we need to compare this to other techniques, like statistical techniques or SVM, or even Camins or just the DBScan, for example. This is one of the reasons why we applied the DDA to know the validity and also to compare with
Okay.
Another question is, are the data sets available?
The data sets most of them are collected from our darknet, which is hosted in Nmrg. To access the data, the guy is there, Jerome. We have to sign an NDA, I think.
Okay, but
So
it
there
is
is a
available.
possibility, but
Okay,
there is some administrative stuff.
okay, thanks.
Joachim Fabini, Technische Universität Wien. Just a note, so darknet in this case is misleading. Darknet means a real region of the internet that is not supposed to be used by people like us. Dark space is a term that is used in literature correctly, and if you search about dark space, then you will find that Qaeda has a Class A network. They're doing dark space research on them. There's a lot of work in this area.
Yes, just one point. Here, the darknet is not the underground networks.
This is why we have the term dark space for this data.
Yes. So it's mainly telescope network, telescope and this. Thank you.
Jochen Kögel, Ethernet. So you looked at the unused address space, the dark space. What do you think if you use other address space and apply the technique to it, like production traffic? There are lots of services and clients traffic. What do you think will be the effect?
I think we can. This is one of the future work that we want to do, is to apply the same technique for, productive networks. It could be packets or even net flows to extract some patterns that will be to extract some services. But we need to find the good parameters for the algorithm, or extract also some scanning activities that targeting enterprise network. So the technique is open. We can apply this not only for the darknet, but it could be for the traffic.
I could just imagine that you find traffic patterns in production traffic which are close to things you discover now. Yeah, like span in, span out. If you have a web server which is occupied by, or which is asked by many clients, and then you have something like a header scenario. Yeah. So it could be, you may end up in more false positives, I guess.
Yes, but in this case, for this specific work, we haven't the knowledge about the data. So we check it manually that this could be the DOS or scanning activities. But if you apply this to real traffic, I think we need labeled data, and then we can check if and we compute this false positive and the accuracy of detection technique. But here we received this traffic from the darknet, so we don't know exactly what kind of traffic. It will be DOS or whatever. So yes, in this case, the validation is a little bit.
Yeah, for dark space, it's quite simple, the validation, because there will be no production traffic, so you can isolate your effects. And if you have production traffic, it's maybe just much more complicated and complex to isolate. What do you want to say?
Have to check.
Yeah, just a comment.
Yes,
just curious.
This is an ongoing work. We are working on this. Yes. Okay. Good point. Thank you.
Any other questions? No? Okay, thank you very much.
Thank you.
Last week, but before the break, it's Marcelo Santos, right? And if I understood correctly from Ricardo, Stinio is your supervisor. That's right. One question, the blue sheet is still circulating? Everybody writing their name? Okay, can you forward it to the... Yeah. Yeah, there's another one. I would like to this look and make a copy.
Okay, morning. My name is Marcelo Santos. I am a professor in Brazil. And the objective of this presentation is talking about some SDN placement challenges. So probably everybody here heard about SDN. The objective is not is a class about SDN, but a brief review about SDN. It's important to have in mind that we have a separation of the control plane and the data plane. In this case, we have entity called SDN controller, and it's a centralized entity. In a nutshell, SDN is a paradigm that decouples the control plane from the data plane. So we have this famous figure. In a summary, we have three layers: the network elements, the data plane, the control plane, the SDN controller, main softwares like POX, Knox, Floodlight, Open the Light, and so on, and some SDN applications that will run over the controller. So we need to have a different view about how to treat scenarios of optimization when we think about SDN. We have now a single point of failures, and we need to think about dependability analysis in a different way. We will have overhead mainly in the SDN controller, and we need to think in a different way about planning and provisioning. And we have some problems like the flow setup time, and we need to think about where to place the SDN controller in the best way, because probably most of the people here knows that, but when you have a switch and a new flow arrives in this switch, if we don't have a specific role to this new flow, we need to consult the SDN controller, and it took some time, some additional time. So we have a lot of research questions related to this scenario. For example, what is the best placement position for each SDN controller? What is the cost of each controller? What should be the capacity of each controller? What should be the capacity of each controller? How to manage the rules and the network policies in a centralized way? How to deploy virtualized SDN controllers, and so on. So how to categorize these problems in an easy way? We propose in this presentation and probably in a draft three main placement problems about SDN. SDN controller placement problem, SDN rule placement problem, SDN hypervisor placement problem. I will start talking about SDN controller placement problem. It's a famous problem, and in summary, SDN controller placement problem, or CPP, deals with the allocation of SDN controllers in a network. It seems an easy question, but it's not. When we think about this problem, we need to decide how many controllers are required to core a network, where to place each SDN controller, and what is the controller domain. In other words, in this figure, in the right side, we can see the controller 1, and we have a lot of switches assigned to this controller, and it's a domain. So when we think about optimization and objective function, it's not polynomial problem. It's an NP-hard problem, and we have several papers about this problem. Like if we quick search for SDN control placement problem in Scholar Google, we can find hundreds of papers about this problem. One of them, like in the first result, has more than 400 citations. And it's not a new problem. Like this paper is from 2012. So the second problem is SDN rule placement problem. it seems similar to the last problem, but it's not. Um, when when we have applications running over the controller, and when I talk that it's not one application but several applications, we need to run the conflicts. We need to decide the best path, and it seems okay, old problem. But think about that. Uh, with with SDN controller, with SDN paradigm, um, we can think about how to do the load balance at the same time, save energy, turn off some links, and aggregating some flows in a specific link, and everything in a real time. It's not an easy problem to solve in a real time when you have a huge network and several nodes. So we have different types of rules like access control, routing policies, traffic shaping, traffic engineer, load balancing, and we need to do everything in a real time and handle conflicts and policies. So we can think about this problem like optimization problem and use some techniques like interlinear program or some heuristics. Um, so the last problem is SDN hypervisor placement problem. In summary, hypervisor placement solutions deals with how many hypervisor instances are needed and their position. It's very similar to the SDN controller placement problem, the first problem that I talked to 2 minutes ago. So here is an example with FlowVisor, or I can talk about FlowN, or doesn't matter. We have a hypervisor, and the hypervisor will create abstraction for each controller in the infrastructure. Like we can have Knox and open the light and floodlight work in parallel. And uh, it's similar to the controller placement problem, but the placement of the hypervisors demands detailed investigation because some question arise like where to deploy the SDN hypervisor. We need to think about hypervisor reliability and fault tolerance because we will have another layer of software, the scalable hypervisor design, and okay, I talked about some problems and I tried to define some problems about related to SDN, but the question is how to solve these problems. What is the best technique to solve these problems? And the answer is it's there is not a best technique because it depends of the objective and the complexity of the network, how many nodes do you have, and how many research you model. So in summary, we have two categories, two categories. Exact resolution methods that give us optimal solutions, and we have a time consume, well, a high time consume. Example of techniques is branch and bound, dynamic programming, and linear and integer programming. We have here a trade-off because we have exact methods to solve these problems, but they will take time. On the other hand, we have heuristics with quasi-optimal solution, um, reasonable computation times, like some techniques like genetic algorithms, simulated annealing, and ant colony optimization. Um, so, one normal question that arises from this presentation is, okay, I have a SDN placement problem. What is the best technique to solve this problem? That is not the best. Here is an example. We have a paper published in the Triple I communication letter, and this paper is from 2012 and use a linear program to solve this problem. We have a model, and here we have another paper, and in this paper, dynamic controller provision and software-defined networks. the other others propose heuristic-based simulated annealing for the same problem. But in this case, we have dynamic placement. So we need to have quick solution. We need to generate a quick solution, almost in real time because it's a dynamic. I analyze the loads in the network and decide where to put and where to create a SDN controller dynamic. So the proposal is create an informational draft, identifying SDN placement problems, challenge, and solution directions. And that's it. Thank you.
Okay, so this was a presentation quite different from the others. The others were presenting solutions, while you are presenting a problem you are working on. So maybe it would be a good idea to for questions or for what do you think? Is there anything important missing? Do you have some feedback to give? Some hints where to how to start, and so on. You think anything? How the problem has been looked at? What do you think? Is it a good idea to look at the problem with the three placement? Placement of the controller. How do I say it? Is from if I ask the audience, is this a good idea? Is there to target this problem? No, really? Okay.
Anthony Lambert. Yes, from a point of view, it's quite interesting because actually, yes, this is a problem for SDN placement, but this is also a problem we find in other topics related to network management. For instance, in my company, we work in optimizing, let's say, monitoring infrastructure based on containers with hypervisor. So you have to do quite the same thing. You have to optimize the way you allocate resources and place them. And this is also a problem for, I guess, in data centers with VMs, etc. So there is a lot of problems with the same background optimization issue. So it's quite interesting to tackle such an issue in Nmrg, I guess. So, yes.
Thank you.
So I'm just relaying a question from Carlos Schmidt. He's asking, how can network measurements help in solving problems you raise in this presentation, and where the measurements should come from? Yeah, so how can network measurements help on solving the problems you raise in your presentation, and where shall you measure those?
Okay, it's a good question. It depends how to treat the problem. We can treat the problem just in an analytic way. The measurement of the network can be an input in the problem, and how to measure that after the solution is generated, it depends of the problem. Each problem needs different treatment.
Thanks.
Okay. No more remarks or questions? Okay. Thank you. So we will have now a short break of around 20 minutes. So we will continue 5 to 11. So you see we have a very precise time plan. And then we will continue with the three next presentations. You will notice that the next three presentations are from industry, from companies and institutions, while the first three were from universities. So let's see what will come up interesting. Thank you. See you in 20 minutes. So welcome back to the second half of the workshop. Thanks again to Giovanni, who is taking care of the Java room. So let's start. Our next speaker. Our next speaker is Marco Davids from SIDN. And please go on.
Okay, we're all seated. Can everyone hear me? Everyone in the back too? Okay, hi. Okay, better like this? Okay. Hi everyone, everyone seated? Hey, my name is Marco Davids and I work for SIDN Labs and we are the R&D team of the Dutch registry. So the registry running the country code top level domain. And I may be representing the industry as Ramin said so nicely, but we are a not-profit organization, just to make things clear. And today I would like to talk briefly with you about our SPIN project. The SPIN project stands for Security and Privacy in the Internet of Things. It's a project we started recently at SIDN Labs, and it's about the Internet of Things. Now, I could argue with you about what the definition is of the Internet of Things. We have been struggling with that internally quite a while. There is a great definition of the IEEE organization. It is only 86 pages long, so you can have a look at that if you like. But I like the approach of RFC 7452. But whatever the definition is of the Internet of Things, we all agree that there will be plenty of it. There is a lot of IoT coming towards us, both in our homes as well in the enterprises. There are many research activities trying to estimate the growth. Here is one made by Gartner. The figures may differ, but everyone agrees there's going to be a lot of IoT. And with that, we will also see quite a number of problems, because all these devices entering our networks, many of them have their limitations. Like, for example, they are cheap, manufactured cheap with poor security. They have standard passwords, hard-coded passwords, telnet ports being open. Sometimes you can bypass security by just going to a direct link. So in general, there is this agreement that it's a bit of a mess and also a security nightmare. And we have also seen evidence of this. This is the famous Nmrg botnet that you may have heard of last year, targeted against Dyn. We were particularly worried about this because Dyn is a DNS provider, and we also run a DNS infrastructure for .nl. And this attack brought many important services down, such as PayPal, Spotify, Netflix, you name it. And since we also run this DNS, a DNS infrastructure for .nl, this particularly triggered us. So we came together, we had this little brainstorm session, and we thought, like, what could be the solution to this problem? Should manufacturers deliver better products, or should we have legislation or international policies, or maybe even certification programs for devices? Or should we make the user more aware? Should security become a feature that sells, that there is a market demand for security? Or should we empower the users to give the user tools to be aware of the things that are happening in his home network, and give him control of what he can do within that home network? So yeah, we came to the conclusion that there is no silver bullet. Actually, we have to do all of these things to solve this problem. But for this SPIN project, we decided to focus on the empowerment of home users. We particularly targeted the home users because we believe that in the enterprise world, there's already a lot of things happening with intrusion detection systems and stuff like that. But if you look at the home user with his router, all a CP device or a home router basically has is a simple manner of defining some firewall. So that's how the SPIN project was born. SPIN is a research project from our labs team, and it attempts to research the user empowerment part. And that means that with our SPIN box or SPIN system or SPIN device, we hope to detect anomalies in the home network. Just to give you an example, it's not normal if your refrigerator starts sending out millions of emails all over the world. That's not typical behavior for a refrigerator. And it's also not normal if your IP camera starts scanning port 22 all over the world. That's unusual. Then what we would also like if once these anomalies are detected, that they are automatically blocked. So suspicious traffic from and to Internet of Things devices, we hope to automatically block them. And we also want to inform an average user about that. I mean, not every user is tech savvy like you are. There are many users who have very limited knowledge about how these things work. We want to inform them and also give them the ability to define some sort of security preferences for this network. So these are the research goals for this project. Our main motivation for starting this project, because it's a little bit out of our league perhaps, is we want to protect the infrastructure of operators, of DNS operators, of other operators. In particular, of course, our own infrastructure. We have a direct benefit if this problem gets tackled in one way or another. We also have this good of the internet mentality, so we would also like to give users more control over their in-home Internet of Things network. And by doing these things, we hope to preserve the trust in the internet, and that's more or less an indirect goal that will benefit us all and also ourselves. We decided to choose for what we call a user-centric approach. That means we would like to allow users to easily deploy a solution. And I'll get back to that later. We want to protect the user's privacy by keeping things local as much as possible. What I mean by that is we do not want to connect to any cloud servers to transfer all the behavior that is going on within the network, because we believe that is a privacy infringement. So we want to do as much as processing on the box itself as possible. And again, as I said earlier, we would like to allow the users, an average user, not the tech-savvy ones, to configure the system according to certain security preferences. And what we are also thinking about is to initiate some sort of collaborative initiative to work together with a group of maybe security related people to define perhaps certain security profiles. Think of a security profile that matches a smart TV, for example. A smart TV has a certain behavior, and it would be odd if a smart TV would be sending out these emails. So maybe we can define templates that a user can load into the SPIN device for specific devices. Maybe in an automated way, maybe in a manual way, I'm not sure. But the collaborative attempt is also part of this project. Here is a brief overview of the SPIN concept. It's hard to see, I suppose, but what this figure represents is a piece of hardware, a device that you install in your home network. It has incoming traffic, it has outgoing traffic, and it has a number of modules. The three main components of this thing are the three modules on the left. A module to visualize traffic, to let the user, to make the user aware of what's happening in the network, and also that there is a control panel there that allows the user to configure certain settings. There is a module that is supposed to monitor devices for odd behavior, and there is a module to control traffic, basically firewall. What this figure also shows is these groups of people on the left and the right. These are the communities feeding the system with knowledge about certain devices, like, for example, your refrigerator or your television or what have you. And again, as I said, the processing is done locally, so the device is not sending behavior of the user to a cloud service of any kind. It's processed locally, and hopefully we will manage to make this largely automated. Of course, this is a provocative thing. I'm aware of that. It's tricky to have a device that have things blocking automatically, but maybe if the profiles are mature enough, we can achieve this goal as well. Yeah. At the moment, the Spin project is both a concept and running code. We decided to start writing running code from the start. So we have at the moment a prototype running. It's based on OpenWRT. And it is also currently bundled with our ValleyBox device. That is an earlier project of SIDN Labs. It is this piece of hardware on the left. It's a GeoINet, small, cheap, kind of home router device. And with the ValleyBox project, we implemented a validating resolver on that thing with trust anchor management, etc. And we took that project to enable Spin on it. So we have enhanced the ValleyBox software with Spin functionality. And one of our architectural principles is to focus on IoT devices with what we call a predictable behavior. So we clearly distinguish between a home computer, a PC, or a laptop, for example, or a tablet, because the behavior of such a device is pretty unpredictable. I mean, my behavior at my laptop is totally different from the one of my wife, for example. I do weird stuff. She just